What's one way that we show relations between two sets of information or two variables, an independent and dependent? Or what's one way we show a function? Graphs. Graphs are nice because it's a visual way of looking at a relationship. And for many of us, visual way is easy to understand. So all I want to do in this is, let's make sure we know how to read a graph, and let's see if we can graph a situation that you're given. Okay. The first one, we've got a relation between, or first of all, it's a scuba dive, and the relation is between time and depth. And you can see this is what's happening. So here's the start of the dive because time is 0. Here's the end of the dive. And then this is all showing the depths that she is reaching at certain points in the dive. First question, how many minutes did the dive last? Well, you got to, basically to answer this question, you have to understand scale. What is each grid line going up by? On the horizontal axis, what are we going up by? 2's. Because if the second one is 4, then the first one is 2. So we're going 2, 4, 6, 8, etc. But we don't want to write every single letter or a number, pardon me. That's why we write every second one. So it ends here. So we just have to know the value of this horizontal axis here, which is what? 30. So it lasted 30 minutes. What times did the diver stop her descent? How do you know when a descent is stopped? There's a horizontal section to the graph, right? Because here at 12 meters, it's continuing at 12 meters for a while. So not going up, not going down. Same here. So we would say, okay, at 4 seconds, she stops. Sorry, at 4 minutes, she stops for 4 minutes. And then at 10 minutes, she stops for another 4 minutes. So at what time? So it would be 4 minutes and 10 minutes. Part C, what's the greatest depth she reached? How would we read that? I'd have to read the y-axis, wouldn't we? The vertical. Anybody? 20, right? Because remember, this is kind of going like, as this goes up, the deeper she goes. But we don't go down like that just because she's going down. The depth increases, so it's 20. And meters this time. And how long did it take her to climb from the greatest depth, which we now know is 20, to the surface where the depth would be 0? Well, here's where she started ascending, climbing. So if we go down here, we can see it's at 14 minutes. We already know she hits the surface again at 30 minutes. So I just need to find the difference between 14 and 30. So 30 minus 14 will tell me how long it took her to get up, which is 16 minutes. See if you can answer the ones on the next page, the next example. Then we'll do that unit circle quiz. How many panicked? 1, 2. Okay, well, I apologize. I sent the Teams message to the grade 11s, but I meant to also send an email message to the grade 11s. I realized it was to the grade 10s. Surprised nobody contacted me last night. I guess you guys are all early risers. Am I recording? Yeah, I'm recording. Okay. So for this one, the relationship is between the mass of various bags of popcorn and the cost. And notice here, it's a series of points. They're not connected. Why would they not be connected? Can you think of why? Like, why wouldn't we just go like this or something? No? Because popcorn are only certain sizes, aren't they? If there is no popcorn size that is 500.7375 grams. There's no fractions. So that's why we put a series of points and we don't connect them. So which bag has the least mass? Anybody? Come on. Least mass. B. And that mass is what? Well, you gotta understand your horizontal scale. We are going up by 200s. So B is between 400 and 600, which should give us 500 grams. Yep. I forgot question what? Oh, that was B. So I like to do things in a different order. Give me a break. Yeah. I ask you guys a question, nobody wants to answer, but boy, I make a mistake, all of a sudden everybody's talkative. Which bag is the most expensive? C. How much? $7, nice. We already got the least mass. Which bags have the same mass? Right? A and E are the same cost. A and E would answer question part D. So D and E have the same mass of 1,800 grams. And the costs are A and E, and they each cost $4. And finally, looking at C or D, which is the better value for the money? Why D? Yeah, you get more for less. First of all, there's more popcorn than C, and it costs less than C. So it makes sense that it's a better deal. So D would be the better deal because, yeah, you get more popcorn for less. More popcorn and cheaper. Okay, so that's a couple of examples of reading information off of graphs of relations. What if you were asked to describe what's happening in a graph? So here, I mean, I could ask you questions about this graph, like we did on the first example. But another thing I could ask you is, tell me everything that's happening in this graph. So first of all, we got to figure out what's going on. We're driving from Winnipeg to Winkler. Okay. So we're starting at Winnipeg at time 0, and then we're going up by, looks like half an hour. And then as we leave Winnipeg, our distance from Winnipeg increases until we eventually reach Winkler, and then it comes back down until we get back to Winnipeg. But we want to say what's happening at every section. So I want to say what's happening at this segment, this segment, this segment, this segment, and this segment. And notice they're labeled with letters. So we can say, okay, what's happening at OA? Well, we leave Winnipeg. And I'll just put WPG. Drive at a constant rate. For how long? For an hour. And how long did we end up actually driving? Well, it looks like 65 kilometers. No, you don't really have to put that. Why did I say constant rate? Why did I add that phrase in? What if from O to A, it looked like that? Could I say constant rate? No, you can't. Constant rate means it's a straight segment. You don't change speed, which is obviously pretty hard to do, especially if you're going through a small town where you have to slow down. But this would not be a constant rate. This means you would start out slow and then start accelerating. So I do want to make sure I say constant rate. What's happening from A to B? What's that? Somebody said nothing? Stopping? For how long? Well, remember, every notch, every grid line is a half hour. So this is half a grid line, right? So it would be half of half an hour, 15 minutes. So we've stopped for 15 minutes. Maybe to grab a coffee or something like that. But then at B, we start up again. So from B to C, we drive at a constant rate because it's a straight segment. And how long do we drive for? Well, 15 minutes, then an hour, so an hour and 15. Is that right? No, that's wrong. 45 minutes, thank you, because every grid line is half an hour. So 15 minutes to this grid line and then half an hour to that grid line. So drive at a constant rate for 45 minutes. And we could say how far we drove, or we could just say, I mean, what's happened here? We've arrived in Winkler. And what's happening from C to D? Well, we're in Winkler. But we should say how long we're in Winkler for. In Winkler for how long? Two hours. And then finally, we leave Winkler. So from D to E, drive back to Winnipeg, because we don't stop this time. drive back to Winnipeg at a constant rate. For, how long does it take us? Looks like it takes us 2 hours. Yes, because it's at the, we leave at the 4-hour mark and we arrive home at the 6-hour mark. So for 2 hours. So there's another thing you can do with interpreting graphs. The last type of example I want to talk about is, now you're given this and you have to create the graph. So here is an example where you are given a situation and you have to come up with a graph of that situation. So we've got two variables here. We always have two variables in a relation. Sam's going on a bike ride, and time is one variable and speed is the second variable. So we're going to put time on the x-axis, or the horizontal, and we're going to put speed on the vertical. So that's the first thing that we can do, is draw our axes and label them. So we've got speed in kilometers per hour, I believe. Kilometers per hour, yes. And we've got time in minutes. When you are graphing a situation, you need to draw the axes and you need to label. You must label the axes. So that's the first part, is to set up your grid. Notice I could start, like have two arrows starting from the bottom left, going to the right, and then going up, because all the numbers are positive. This is like drawing the first quadrants of a coordinate grid. Like 4 quadrants is normally like that. We've just drawn this one because everything's positive. There's no negative speed or negative time. So we don't have to draw all 4 quadrants. But the next thing we have to do is figure out what the scale is. For speed, how do we figure out the speed? Well, what's the highest speed he reaches? 20, right? So our graph, our vertical axis has to start at 0 and go up to at least 20. We've got to have enough room. I can't go up by ones because there's not enough. Right? If I went 1 kilometer an hour, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I could only get up to 15. So what maybe do you want to go up by? 2s. So 2. First of all, this is 0. 2, then 4, 6, then 8, 10, then 12. Notice I'm not doing, I mean, if you want to label every single notch, every single grid line, you can. But it's good practice to do every second one. 14, 16, 18, 20, 22, 24. I don't even have to go that high because it just never reaches that high. So we'll be able to graph the speed part because the highest is 20. Now we got to figure out the minutes. How are we going to figure out how to scale the minutes? Well, we got to figure out the whole length of the bike ride, because then that will be the biggest number. So he starts at 2, then he goes for another 30 minutes, so that's 32 minutes. Then another 3 minutes, so that's 35 minutes. Then another 10 minutes, so that's 45 minutes. Then another 2, so that's 47 minutes. And then at a full stop for 10 minutes, so that's 57 minutes. We have to go up to at least 57. Well, let's make it a nice round number, 60. So we have to get up to at least 60. What could we go up by? Any idea? Can't go up by 2s, we won't reach it. 5s is good. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Now that we've scaled correctly, we should be able to draw our graph. So now we go back to the story and graph it. Well, we're going to start here at 0. What's the first portion? He cycles, he accelerates for 2 minutes at a constant speed, so that means it's straight, until he reaches 20. So that means he's got to go for 2 minutes along here, but get up to 20 here. So this is 5, so it'd be a little less than halfway. So it's going to be a really sharp climb to start. Okay, so we've done that. That's taken care of. I know, it's stunning. He reaches a speed of 20, and then he stays at that speed for 30 minutes. Well, if he stays at that speed, I'm going to be drawing a bar across, a segment across, but I got to make sure it lasts for 32 minutes. So we've already done 2, or sorry, for 30 minutes. We've already done 2. So this would, I'll go up by 10s. This would be 12. No, wait. 2 and 7. Yeah, 12. And then 22. And then 32. You should be somewhere around there. Is that the, yeah, that, wait a minute. Is that right? Did I get that right? 2, then 12, then 22, then 32. Yeah, I got that right. So like so. So that portion is taken care of for 30 minutes. Now he's coming up to a hill, so he's going to slow down, and it takes him 3 minutes to decrease his speed to a constant rate of 5. So 5, he's coming all the way down here, because it has to be halfway between 4 and 6. And he does it for 3 minutes. So he should be right about here. Only 3 minutes. And now we're at the 35-minute, oop, missed that one. Now we're at the 35-minute mark. So we've taken care of that. Took care of the 3 minutes. And then he sticks at that speed for 10 minutes. So here he sticks at this speed for 10 minutes. Well, that's pretty straightforward. 5, 10. He'll be here. Then it takes him 2 minutes to decrease his speed until he reaches a full stop. So 2 minutes is less than half a grid line, and then he's at a full stop. So he's at 47 minutes. Now, technically, we're done, but it does say at the end, he stays there for 10 minutes. So we're going to have to add this. Then the situation is over. And we've accounted for everything. That is something you should be able to do. Okay. This last one is kind of like you come up with the situation. Can you think of something that this graph would fit? So you've got to think of two variables that relate to each other. What are variables that are, what variables did we use quite a bit? What variable did we use quite a bit on the horizontal axis in the previous example? Time. Time's a good one. Time's always a good one. Doesn't have to be the only one. And then for the vertical, it could be things like distance, height, weight, or mass, or something like that. So can we come up with a situation? Can you come up with something creative? Like, what's that? Plane? Okay. So what's happening? What's happening at the beginning of this situation, your situation? But if it takes off, it should be down here, shouldn't it? So you can say your situation starts while the plane's in the air. Okay. Then what happens? It rises. So this is going to be your height. So the plane is at a certain height. And then after a certain amount of time, it climbs to another altitude, stays at that altitude, and then goes up and out of the atmosphere. Sure. Yeah, space plane. Yeah. Yeah, that'll work. Okay. There's really no wrong answer here. I mean, for me, I think of time and student stress level. So, you guys are sort of at a certain stress level. And then maybe you've got a lab due. So the stress level goes up a little bit. Okay, sort of stays at that until you get the lab done. And then you are told that you have 2 tests the next day. So the test level or the stress level skyrockets. Could be anything. Okay. Another one I like to look at is, what if I gave you this? This is always an interesting one. Can you come up with a situation where it's, you can always use time. Your mental health? So you're on a bit of a roller coaster ride? Okay. Sure. How would you measure, by the way, how would you measure your stress level or your mental health? Like, we'd have to have some kind of measurement, wouldn't we? Like some kind of, I don't know, measures brain function or something like that? Or whether a certain portion of your brain is flaring and in certain units. Yeah. Anything else? What's that? Nothing. I heard toothache. Was I hearing things again? Yeah. Well, I haven't heard voices for like a couple of weeks, so I thought it was okay. But I guess now I am. What's that? Wait, you can see me? I've always wanted to do that in a grocery store if somebody talks to me. It's like, wait, you can see me? How about a swing? Well, you kind of go up and down. That's what swings do. I mean, if it went like this, if I went like this, yeah, that might be a little bit scarier. But it's kind of over a little bit of time. So it's not that scary. How about and we'll actually get into this more in grade 12 because what I just showed you there was a trig graph. What would a ride on a Ferris wheel look like if this was time and this was height? So would it look like this? Remember, this is time, this is height. First of all, the height is at 0. It's going to be tough for a Ferris wheel to get off the ground at 0. It's got to be a little bit above the ground, okay? And second, if it goes like this means that this Ferris wheel, it climbs up, and then it goes back in time and comes down. And then time moves forward again, but then we go back in time. So it doesn't quite make sense. A Ferris wheel would look like the one that I just drew with the swing. It would look like this. You start at a certain height off the ground, you climb, reach a certain height, you come back down to the bottom, and then you climb again, and you come back down to the bottom. That's the path of a Ferris wheel. Many things we can model with this kind of shape. Okay, I'm going to leave it at that. Save